Hey, welcome to the Explainer. Today, we're going to crack a classic university physics exam problem. You know the type, where you've got all the data, you know exactly what's happening, but the one formula you're sure you need, well, it's just not going to work. So what do? This isn't just about crunching numbers. It's about thinking like a physicist and seeing the hidden connections between all the concepts. So let's dive in and solve this thing together. All right, like any good detective, our first move is to lay out all the facts of the case. What information are we actually working with in this so-called constant pressure puzzle? Okay, here's our evidence board. The process is happening at constant pressure. We've got 5 moles of an ideal gas, and its temperature shoots up by 10 Kelvin. We're also given these two strange clues, CP and CV. Our mission, should we choose to accept it, is to find the work done by the gas. This is the big question, right? We've got all our evidence lined up, but where on earth do we even begin to calculate the answer? Now, for any process at constant pressure, what physicists call an isobaric process, the first thing that probably pops into your head is this formula. Work equals pressure times the change in volume. Simple, direct, and yeah, usually it's exactly the right tool for the job. And here's our first major roadblock. If you look back at our evidence, there's no P, and we have absolutely no clue about the initial or final volumes. So yeah, that standard formula, it's a total dead end. We can't use it. This is where the real physics thinking kicks in. When one tool doesn't work, we gotta find another one. We need a different angle, a new way to connect what we do know to what we're trying to find. And here it is, our big breakthrough. Remember the good old ideal gas law, PV equals nRT? It's the key that connects pressure, volume, and temperature. For a process where pressure is constant, it means that P times a change in volume is the same as N times R times a change in temperature. This gives us an entirely new path forward. Since work equals P delta V, we can just swap that out and get a brand new formula. Work equals N times R times delta T. This is awesome. We already know M, the number of moles, and we know delta T, the change in temperature. But hold on. We've just traded one unknown for another. The problem never gave us the value of R, the universal gas constant. So how do we find it? It has to be hiding somewhere in the data we were given. And that brings us to the real heart of this puzzle. The secret to finding R is locked away in those 2 bits of data we haven't touched yet, the specific heats, C sub P and C sub V. Okay, so let's break these down. First up, CV. That's the molar specific heat at constant volume. I want you to imagine heating up a gas that's trapped in a sealed, rigid box. CV is simply the amount of energy you have to pump in to raise its temperature by 1 degree. That's it. A great way to think about this is with a little analogy. CV is like the base price of fuel. It's the pure, raw cost of the energy required to make those gas molecules jiggle around faster, which, is all temperature really is. Now let's look at C sub P, the molar specific heat at constant pressure. This time, picture the gas in a cylinder with a piston that can move up and down. As you add heat, not only does the gas get hotter, it also expands and pushes that piston up. So, back to our fuel analogy, CP is like the price of the fuel plus a tax. You're still paying that base cost to heat the gas, but you also have to shell out a little extra energy, a tax if you will, to do the work of pushing that piston and expanding the volume. So it's pretty clear, right? CP is always going to be bigger than CV. They both contain that core energy just to raise the temperature, but CP has that extra chunk of energy that goes into doing work on the surroundings. And here is the absolute key, the whole point of this. That difference between CP and CV, that extra tax you have to pay for the expansion work, well, that value has a name. It is R, the universal gas constant. R is literally the expansion tax. Okay, we have all the pieces now. We've got our formula, W equals NR delta T, and we know exactly how to find R. It is time to put this all together and crack this case. All right, from here on out, it's just a few simple steps. Step 1, find R. We just subtract CV from CP. 25 minus 15, that gives us 10 joules per mole Kelvin. Easy. Step 2, grab our new formula for work. Step 3, plug in the numbers we know. 5 moles for N, our newly found R, which is 10, and 10 Kelvin for delta T. And finally, step 4, just solve it. And there you have it. 5 times 10 is 50, times 10 is 500. The final answer is 500 joules. That is the total amount of work that the gas did on its surroundings. And you always want to do a little sanity check, right? The temperature went up, which means the gas had to have expanded, pushing against its surroundings. And when a gas expands, it does positive work. Our answer is positive, so check. It makes perfect physical sense. But look, getting the number 500 isn't really the big win here. The real takeaway is about how we got there. It's about the approach, the physicist's mindset. It really comes down to this idea right here. In physics, formulas are just tools in a toolbox. The real skill isn't memorizing all the tools, it's understanding how they all connect to each other. So I'll leave you with this question. The next time you're staring down a problem that seems impossible, don't just hunt for a single formula. Look deeper. What are the hidden relationships you can spot to forge a new path to the solution? Thanks for joining me.